I'm going to do a real quick review of the domain of functions. There will be several functions that we just briefly look at right here on this slide. So let's get started. First off, across the top of each one of these columns, I'm just going to state the domain of these functions. Linear functions will be in the group with the set of all real numbers as their domain. You see these functions that are being listed: the quadratic, the cubic function, the absolute value function. All of these functions will have a domain that is the set of all real numbers. Okay, and just real quickly off to the side here, just a brief sketch of those functions. Notice how they are continuous. There are no gaps, breaks, or holes in those functions when you graph them. In this next column, well actually, down at the bottom I left one off, the cubic function, cube root function. It also has a domain that's the set of all real numbers. Alright, now we're here in the middle column. This is our reciprocal function. Notice that there is a break. It is undefined at the domain value of 0, which is your x value. We have to list that as a restriction. So anytime you have a function where a variable shows up in the denominator, you're going to have to check to see if that is in fact a restriction. In this last column, we have the square root function. Remember, you can't take the square root of a negative number, otherwise you will get an imaginary number or a complex number. And right now we're just focused on numbers, real value numbers. Okay? I'm going to go back through here and I'm going to label each one of these axes correctly. I went through pretty rapidly and neglected to label those. So we'll let that finish up there. The real brief review of domain of our basic functions was done in order to go over some of these composite functions that we're about to look at. So you're going to be given two functions. Here, this one is a linear function, and g of x is going to be a quadratic. Okay, the notation for a composite function is this symbol here, f composite g of x. Okay, notice the little open circle. That's not to be confused with the multiplication symbol. So here the first composite is going to be f composite g of x. So wherever in f there is an x, we are going to now substitute in the g of x function. And so there you see I left off the x from f of x, where I have the highlighted blue area. That is going to be filled in by g of x. Again, since the domain of f, or the domain of f is the set of all real numbers, and the domain of g of x is the set of all real numbers, because f is linear, g of x is a quadratic. So we simplify this quadratic here, and there's not much anything else we can do with this. And the domain of that composite is just the set of all real numbers. All right, this next example is going to be a little more involved than the first one. Here, both of these functions are going to be reciprocal functions. That creates a lot of issues because of the variable in the denominator. So at this point, you're going to be asked to find the composite and state the domain. First off, we're going to find the domain of each individual function. Here we see that for f, x cannot equal 1, and for g, x cannot equal 0. So as we form the composite, notice that wherever there was an x in the function f, I left it blank because I'm going to substitute g of x. Now this creates a nice little mess in the denominator. So what we have to do is we have to focus on identifying the restrictions first before we simplify at this point. So initially we see that x cannot be 0 because 2 over x has to be defined in order for the rest of the composite to exist. So we immediately know what that restriction is going to be. Now, for the other one, we determine that algebraically. So off to the side here, I'm going to say, well, I know the overall denominator of 2 over x minus 1 cannot equal 0. Then it just becomes an algebraic manipulation here where we solve for x, and we see that x cannot equal 2 as well, because if I let x equal 2, I plug that in, even though it satisfies 2 over 2, well, that simplifies to 1, and 1 minus 1 is still 0 in the overall denominator, and it still is an undefined function. So from the algebra side of it, now we're just going to work on simplifying the denominator, cleaning everything up, and just kind of follow through with the math here. All right, so here I have 3 over 2 minus x over x, because just like with any fraction, you always have to have a common denominator. Because there's a denominator in, or there's a fraction in the denominator of the overall composite, I'm going to multiply everything by the reciprocal, and then when it all shakes out, on this next slide right here, you're going to see what the final composite will look like. And we'll also include the domain restrictions. Okay. So hopefully that helps you work through some of the more involved composite functions. And thanks for watching.